Keep going. Phenomena of enormous magnitude manifest themselves when the criteria for voltage or potential difference is instantly discharged. This is how Tesla managed to create the special type of oscillating and impulse currents that he used in his technology. We'll see about these later. The effect is analogous with the open circuit of inductive current. Because the forcing voltage is instantly withdrawn, the field explodes against the bounding conductors with a velocity that may exceed light. Because the current is directly related to the velocity of the field, it jumps to infinity in its attempt to produce a finite voltage across zero resistance. If considerable energy has resided in the dielectric force field, again, let's say several kilowatt hours, like in a household daily use, that quantity of energy, the resulting explosion has almost inconceivable violence and can vaporize conductors of substantial thickness instantly. Dielectric discharges of great speed and energy represent one of the most unpleasant experiences the electrical engineer encounters in practice. When you're dealing with these giant phase-advancing capacitor banks in these substations that connect the grid together, is if those things stay charged, is if you don't drain the resistor, if you try to short that thing out, the glass will just basically blow your eardrums right out and blind you. And the energy of the capacitor is nearly instantaneous in its delivery, where the inductance tends to be more of a retarded type of phenomenon. This one doesn't slowly build up. This one slowly builds down. Okay, so let's go on.
Oops, sorry.
No, back one.
Next one.
The powerful currents produced by this sudden expansion of the dielectric field naturally gives rise to magnetic energy. The inertia of the magnetic field limits the rise of current to a realistic value. The capacitance dumps all its energy back into the magnetic field, and the whole process starts all over again. The inverse of the product of the magnetic storage capacity, which we call inductance, and the dielectric storage capacity, which we call capacitance, represents the frequency or pitch. Remember, it's the rate at which this energy interchange occurs. This pitch may or may not contain overtones or harmonics, depending upon the extent of the conductor's bounding energy. So this basically, this part here on the ether is complete. We'll have you answer, let's see, I don't have enough time. We'll have you ask questions on this now, if anyone has any questions. No questions?
Oh, that's a comment.
Okay.
When we were developing power supplies for some of the particle beam weapons that we were playing with many years ago, this idea of giant capacitor banks discharging in essentially near real time was quite well demonstrated.
Yeah.
We blew things up all the time with that very principle, so I can attest to that.
Okay. Well, I can't believe nobody has any questions on something this, everyone understands everything I'm saying?
Oh, no, that's a big percent.
How many people understand 10% of what I'm saying or more? Okay. I think everybody's getting something out of it, though.
Yes.
Okay. Well, as long as I'm not putting everybody to
Well, let me
sleep.
throw one question out since we're talking about this concept. What if you had the potential for time phase shift, even very slightly? You would then perturb dramatically, I would think, the energy quotient potential given reference point in this model. Possibly?
Yeah, that's what, remember when I went back to the, I don't know if we can go back there or not, but when I showed the dimensions of resistance were inductance varying with respect to time, and then I showed the dimensions of conductance were capacitance varying with respect to time, that's the time shift. And what that does is then energy starts to go sideways into a dimensional relationship where it's no longer energy. Its pieces may still be there, but it's no longer, the pieces no longer make the pie, which we call energy. Right. Instead, we just have the can of cherries and we have the bag of flour. They're all still there. They haven't gone anywhere. We can take energy, okay? Now, according to Heaviside's law of the continuity of energy, that energy that exists in this capacitor coil can vanish as long as it exists at another time. But that still meets the requirement for the law of continuity of energy. So this is basically how we get energy synthesized in electrical systems, is by moving it around in time. That's where an alternating current phase is always the #1 word in everything we're dealing with. It's where are you at in the cycle? And you can build electrical machines to do this. I've seen them where energy will go into a generator okay, and the generator will have no load connected to it, okay, and you can have a kilowatt meter, okay, sitting on the input of this generator. Not an amp meter or voltmeter won't give you the real energy flow. It'll give you a false reading. But if you have a power factor corrected kilowatt meter, or I've done it with a kilowatt hour meter, that would have been the proper way to do it. Energy will go into this rotating machine, which varies with reluctance with respect to time, such as an Alexanderson alternator, and the energy will vanish. You'll be yanking power and paying for it from the world. So maybe I'm not just making this up. Because if you want to understand Tesla, you better get all this stuff out of your mind, or you're not going to get one iota of understanding of how Tesla works. You'll be permanently blocked from understanding it. That's my theory of why there's the theory of relativity. But we're not here to talk about the theory of relativity. We're here to get away from it. Okay, now conversely, the dimensions of mass or magnetization are concrete realities. These exist independent of the metal process. Hence, these are called the quantitative dimensions. These are what we apply space. These are what we apply to. We have the number of grams per square centimeter, per cubic centimeter. We have the number of volts per second. Any of these type of things it's always the metrical dimension is attached. That's why we started with the undivided quantities, and then we metrically worked them in time to produce power and voltage, and we metrically worked them in space to produce flux densities over areas. Hereby it can be seen that the metrical dimensions work upon the quantitative dimensions so as to gain a mental concept of the process or actions involved in the quantity. 4 electrical dimensions are required for electrical representation. One is the total magnetic induction. The other is the total dielectric displacement. Our metrical dimensions are time and space. So our 4 dimensions are phi, psi, and then L for length, and T for time. These are the 4 dimensions of electricity. Everything in electricity consists of an interrelationship of these 4 dimensions. In physics, it's mass, temperature, length, and time. In electricity, it's magnetism, dielectricity, length, and time. It's a completely analogous relationship to physics, but it exists in a different reality. Let's take the situation of the gas laws, which we went back to at the beginning. I wanted to draw this up, but I didn't have time. I maybe can do this here. Can I move?
Yeah, absolutely.
Let's, does this paint work? Let's see. So if we have pressure, okay, pressure basically increases with temperature and decreases with volume. So these 3 quantities always have to exist in a relationship. Okay, now if I take a cylinder, okay, and I have gas trapped in here, it has to correspond to the kinetic theory of gases, which this describes. So if I have a constant temperature, if I have a pressure of a certain quantity in here, and I have a temperature of a certain quantity, if I decrease the size of this container, then in order for this relationship to preserve itself, either the temperature has to go up or the pressure has to go up, and consequently, both of them go up. Okay, now if I take a given cylinder, and I put a fire under it to raise its temperature, okay, the pressure will go up, and the temperature will go up, but the volume can't go up. So we have here a situation where these 3 quantities have to be conserved. Now, you brought up the time factor. Well, this is interesting, because this is the important part. Now, if I make this part that we blocked off of this cylinder, a piston in the engine, okay, and I'm introducing a fluid situation in here, like gasoline, and causing it to combust, now we have a time cycle where these things are varying, and it causes what we're going to get into what's called a hysteresis loop. And that way the energy can go in or out of the system, and if you measure the pressure in the cylinder of an internal combustion engine, it will remain constant through the entire cycle. This thing about explosions, pushing the pistons, and all that's a bunch of gobbledygook like electrons flowing in wires. In actuality, the pressure will remain constant because the temperature and the volume are changing, and the ability to keep that pressure constant is what allows the oscillating time-variant cylinder to take the energy from the combustion and deliver it to the crankshaft. And there's various cycles that are called like diesel cycles and what have you. I don't know that much about engine theory. But this is the type of situation we're dealing with. So we have the normally time invariant model, like if we have inductance and capacitance, we can represent that by this energy stored in here. But if we have cyclic changes in those quantities, if we vary them with respect to time, then we start to get out of these dimensional relationships and get into something more complicated, where energy either comes into the system or goes out to the system through some form of translation, either from the ether or from the burning gasoline or whatever type of situation. This is basically what we're trying to get into theoretically, so we can figure out how to produce these electrical systems that tend to be self-sustaining rather than so dissipated, like the power line between the shipyard and the substation. That power line was creating electrical energy because of the fields that were going backwards in time and space out of the shipyard back to the substation, took that electric field and rephased it and turned it into production of energy rather than consumption of energy. So we get back to the, so that's what we're going to try to get into now is more of the mathematics.
Were those lines to the shipyard dual paired lines?
It was 600 amp, three-phase, 12,000 volt power line.
But were they like pairs of lines?
Yeah, they were big, heavy copper cables, two in parallel for each phase. Yeah, roughly talking about 1,000 pounds of copper per span. If you ever stuck anything across those, it'd be the big blue flash. It'd be, I don't know if anyone's ever used acetylene torches, but when you don't give it oxygen, you know those little black flakes floating in the air? That's about all that's left after you tangle with 12,000 volt bus bars.
We've been talking for 2 hours, almost 3 hours. You want to take a 10-minute break?
Yeah, I thought it'd be good.
Okay, we'll take a 10-minute break.
All right.
Thank you.
Yes. Have a seat.
You have a number of books. Which book is
Those
this?
points that I'm pointing until now. The notes that you have.
About algebra. In other words, the way to work with this in the engineering reality, you have to be able to calculate. So what we see here is we look at these rows of pipe, which all represent frequencies or wavelengths in what's called a geometric progression. You can see they don't increase at a steady rate, but they increase in a rate of proportionality that grows or decays. That's what we're looking at. This is what's called a logarithm, or an exponential type of relationship. Instead of 1, 2, 3, 4, 5, which is a linear relationship, what we're dealing with in studying electricity is a logarithmic relationship, more like 1, 2, 4, 8, 16, 32. That would be a logarithmic or an exponential relationship. So these curves are basically the curves that we're dealing with in our study of electricity, but these curves exist in the dimensions of electricity and not necessarily in physical dimensions such as we see with the organ pipes, but the principles are exactly the same. The curvature, or the rate of change. What we're dealing with here is we have to have a mathematics which can express change. This was first developed by Newton and Leibniz in what was called the calculus. But the calculus is very unwieldy for this type of stuff, and a lot of times will not give you meaningful answers. So let's go to the next one. So the archetype of our equations is all based on this form called the conic sections. So if we move our plane of reference, we might call it, through this cone, we have circles, we have ellipses, and we have parabolas. But they're all based on the same form. They just represent a different angular displacement. And as we'll see later, this angle of the plane, we're going to call this in Steinmetz's terminology, the angle of hysteresis. And we'll see later how this comes into being. Let's go to the next one, get another shot of it. So you can see that our equations of the circle, which is the sine wave, our equations of an ellipse, which is like a dissipating sine wave, or a parabola, which is kind of like a sluggish capacitor discharge into a coil. These are all direct, physical, producible situations with geometry. And these are what are called our archetypes that we build our engineering math on. These very simple relationships. If it was taught to you like this in school, you would be a mathematical genius after the first semester.
Is there some reason why you don't have hyperbolas?
That's next.
Oh.
That's what we're getting into. Okay, let's keep going. Okay, so that's another, okay, now we're going to keep going. We have another look at our cone. And these are the cross sections. So these are basically our cyclic or alternating current waves, which are based on circular functions. Let's keep going. The parabola is a crossing point now into another relationship, where we're getting out of the sine waves and we're getting into what are called transient or impulse waves. These are the types of waves that Tesla was using. He was not using sine waves in his later developments. He was using a completely different type of electricity, just as we saw with the flux lines. There's energy storage in outer space, and there's energy storage in inner space. Tesla's technology dealt with the energy storage in inner space, where you're pulling energy from kind of the infinitely small and expanding it out into the presence of where we are at now. Let's keep going. Okay, now if we turn the situation sideways, we get what's called the hyperbola. Now the hyperbola is a type of circle turned inside out. And in this type of graphical presentation, we have to have two cones for the hyperbola, but ultimately we need two cones for the circle too, but this guy didn't do it in the book. Because in any type of alternating current or circular function, there's one wave that turns clockwise and there's one wave that turns counterclockwise. In other words, one's going forwards in time and one's going backwards in time. The inductance delivers forwards in time, the capacitance delivers backwards in time, and the two produce a result. With the hyperbola, these are like impulsive discharges, where there's no oscillatory exchange, but the energy is growing, like the switch is blowing up, or is decaying, like the resistor hooked across the inductance coil, eating its magnetic field, produces these type of curves. But there's always a pair of curves, and we can say that if we have inverse dimension representations like minus time and plus time, then the upper conic would be negative time and the bottom conic would be positive time. But this is very difficult to represent in the spatial representations when it really exists in time representations. But nevertheless, these are our archetypes. These curves are exactly what we must calculate when we're dealing with transmissions of waves down telephones and power lines and inside motors and generators. So let's keep going with some more. There's a side view of the hyperbola. It's a pair of curves that approach each other. And we can call this an inside-out circle is what it is. This is a circle turned outwards into another relationship. We could call it in physics term, we would call this a circle in another dimension. An anti-circle. Let's keep going. There's another, the plane has shifted a little bit. Now we've moved our angle of hysteresis, so it's cutting differently. And then he's got a really good shot here towards the end. There we can see our different types of hyperbolas. Okay, now we're going to start to get a little more abstract with this. As we move along, there's a parabola, and of course if it turns sideways, there's a circle and it just appears a straight line. Okay, and that didn't show up, but that was a drinking fountain making a parabolic arch. Showing that.
You can show it with the laser.
I can see it.
You see it? Yeah, it's kind of there, yeah. Somehow this is all screwed up. It's a disaster. But at any rate, you can kind of see it. Okay, now we're dealing with it more symbolically, where there we have, you go here, we have our axis of angular movement, where we can go from the hyperbolic to the circular functions, and we get our equations where these things all basically are where two quantities always equal unity. In other words, just like the pressure, temperature, gas laws, is the sum of, or the product, the sum of two quantities must always equal a constant. So we'll get a little further down, we got the next picture. So we'll take the circle. Okay, the circle always has a constant radius. No matter where it is, one thing we know is that R always equals 1. Okay, and the way that this part moves and the way this part moves, move it in such a fashion as we go around, one lengthens, this one gets longer as we go around, but this one gets shorter. So this one would be called the sine wave, and this one's called the cosine wave. So this is where our AC waves come from. As the generator rotor is turning, is these projections of voltage and current produce these spiral movements. It's like this thing is moving downwards, and as it goes around, it makes a spiral as it moves. So we have our basic mathematical relationships in this, where these quantities, you take the Pythagorean addition of them, they must always equal 1. That's very important. All the mathematics that we're going to develop henceforth will all utilize the number 1. The number 1 can actually be used as a calculating mechanism of such ultimate simplicity it's beyond belief. This is what's called the S.F.T.S method. Let's go to the next one. Okay, now we have the hyperbola, which is basically an inside-out circle. Now we have, instead of the sum of the two quantities, we have the difference of the two quantities equal unity. So it's a similar situation, but turned inside out. And as you can see, it still has a circle type of reality, but it's only in an expanded type of. It's very difficult to explain these kind of things. And I've been working on it for years, and I still haven't come up with the final thing so you can really make it click in your head. But you can see that one goes outwards and another one is confined. So these variations are what are called aperiodic. In other words, they do not come round and round like the circle, but they go through a basic motion and then they're gone. They come and they go. These are what are called transient electric waves, where the alternating current waves of the circle are continuous electric waves because the rotation is constant and the unit vector is constant. So there's alternating current waves are a continuous wave, where these represent impulses that are discontinuous waves. Okay, go to the next slide. This is represented by this graph represents the velocity of light, which must always remain constant. So that means that this hyperbolic curve, where this represents frequency and this represents wavelength, the product of the two must always equal a constant, which is the velocity of light. So like the circle, the hyperbola has a character to it that has to always equal a constant quantity, and that's what makes it shape. This also could be the Lorentz transform for the relativistic mass increase, and time dilation follows the exact same type of curve, a hyperbolic curve, where you approach something that can never reach it. So in other words, if the frequency goes down and down and down and down and down, then by following that point along this curve, the wavelength has to get longer and longer and longer and longer until eventually when the frequency is down, the direct current is 0, the wavelengths are of indefinite or infinite length. So we have this inverse proportion between frequency. The higher the frequency, the shorter the waves. The lower the frequency, the longer the waves. But they must always equal the velocity of light, and that forces them into this archetype of curvature or rates of change. So here's a basic example of a hyperbola in action. Let's go to the next. Okay, now we're going to, this is the S.F.T.S symbolic method, and we're going to go, what I've done with the S.F.T.S symbolic method over a period of about 8 years is I've extended it hundreds of times beyond what S.F.T.S did, and made a whole system of mathematics out of it to describe all these other type of electrical situations. It's still a little on the preliminary side. It's what Heaviside calls experimental math. Heaviside pointed out that mathematics doesn't really have to be the tight-ass thing that it's normally presented, but you can experiment with it and make up your own mathematics as you go. As long as you can calculate your values from it, that's good enough. And if the mathematicians hate you, then we have an explosion at the shipyard. Okay, so we start basically, we have the number 1 as an indivisible unit. If we take 1 to the 1 power over the first power, that equals 1 and can only equal 1. But we can work with this. If we take 1 to the 1/8 power, or we would say the 8th root of positive 1, we must have 8 roots by definition, even though all these roots equal 1. So what this does is now it starts to break into a polar type of relationship, such as we find in electricity. So I can take the 8th root of positive 1 and break that down into the 4th root of positive 1 and the 4th root of negative 1. So they can either be represented as an exponent or under a radical sign, but they're both the same thing. So the 8th root of positive 1 divides us or gives us 2 poles, the 4th root of positive 1 and the 4th root of negative 1. The 4th root of positive 1 is our circular functions, basically. The 4th root of negative 1 is our hyperbolic functions. So now we've taken these 2 curves and we've begun to express them symbolically. So basically we have 8 roots. One of them is positive 1, one is negative 1. One is positive h, the other is negative h. One's positive j, The other one's negative J. Now this is the Steinmetz method. He uses +1 and -1 for DC, and plus J and minus J for AC, which almost every electrical technician or engineer has seen, is that you always add the reactance to the resistance, where the resistance is plus R, the reactance is plus J times R. I got into this in my last talk. I was referring to how to use these things as operators. So basically, what we've done is we've extended the laws of addition and subtraction to have a more expanded or generalized meaning. So the eighth root of +1 gives us 8 poles of electricity. These we'll call the continuous, and these we'll call the transient. This is the electricity we use today. This is the electricity that Tesla used. Okay, let's go to the next one. We're going to break this down more. Okay, so here's our basic form. Okay, we start from the 8 and we go into pairs of 4s. And we go further.
Next one.
Next one. Okay, so we already saw this. So here we have our 8 poles, because an 8th order equation has to give us 8 results. So basically what I'm doing here, if it's done in symbolic form advanced, is this will allow us to solve an 8th order differential equation without going through all the nightmares, by reducing it to simple algebraic relationships, and we'll see how this works as we go through. Or we will attempt to see, because it's going to be, if you thought it was thick before, it's going to get thicker now. So all I can do is just go over it. Okay, let's keep going. Okay, so here we have basically our 4 real elements, which we will call DC and AC. So this is our continuous waves, and that's represented by the 4th root of +1, and we go on. Then we have the 4th root of -1, which gives our 4 transient elements. So these are our impulse and oscillating currents, as we'll see later. So let's keep going. Okay, so now we break these down even further. So if we take and go one more step, and we take the square root of +1, then that gives us +1 and -1. Okay, so we've gone from these elements, and we see how that can be expressed symbolically. So the square root of +1 gives us our DC. In other words, this is the battery, this is the light bulb. Okay? The absolute value of these always equals 1. Okay, let's keep going. Okay, I think we lost one here, but these are the 8 electrical waves we're dealing with, okay? This is the DC, and this is the AC. But we have all these other electrical forms that are very seldom talked about until the switch blows up, or the transformer catches on fire, or the railway shuts down, and then Steinmetz came in and found there was all these other forms of electricity flowing that evaded switchboard instruments and were very destructive. And Tesla found out a way to harness these into a new type of technology that is completely unknown, even though he told everybody over and over again how it works. Everybody goes right back to DC and AC. But Steinmetz started this mathematical process now where we can show these things in their interrelations. So let's keep going. Okay, so this is the AC wave. Okay, so now the square root of -1. And we have to remember that GE said Steinmetz could create electricity out of the square root of -1. That was very close, but actually it's the square root of -1 to the square root of -1 power. And that's what we're going to get into. It should be a nice Alice in Wonderland. Okay, let's keep going. Okay, so now if we break down more, if we take the square root of +J, then that gives us, starts to get us into what we call impulse currents. So now, let's go back to the AC wave. Okay, this represents the inductance coil, and this represents the capacitor exchanging energy back and forth. So the square root of -1 represents the storage and transfer of energy, where the square root of +1, the DC wave, represents more of the energy coming and the energy going. And we go back to the impulse currents. These are the waves that tend to be transient, where they have single discharges, where a capacitor is discharging or a coil is discharging. So this would be the energy supply, and this would be the energy sink in that situation. But now we're dealing with hyperbolic rather than circular functions. Let's go back to the waveforms. So that would be the waveform. That would be these 2 waves. This area here would give us, which just didn't work, I think the batteries are going dead. These are our impulse current waves. So if this one is plus and minus 1, this one's plus and minus j. You should have 8 waves here. Okay, it seems like there's something extra, but we'll discuss this equal. These are our basic impulse type of waves that we're dealing with. Then we go on. Now the square root of minus j, this gives us plus k and minus k. And of course, the absolute value of all these things always equals 1. There's no quantity here. These are simply what are called versor operators. They give us polarity, but they don't give us quantity. They're like plus and minus signs. In other words, if I take 1 and I add it to 1, I have 1 plus 1. But if I take 1 plus 1, but I put a minus sign in front of the 1 on the second part as an operator, then I have 1 minus 1, and that's what we're doing here. This is an extension of the process of plus and minus out into a polar relationship, where all these aspects of electricity exist in 8 forms. It's 8 forms of electricity in action in a generalized situation. This is